Good afternoon and welcome to the American Floral Endowment's Grow Pro webinar series. I'm your moderator, Forrest Brown. I'm a member of AFE's Young Professionals Council and a PhD candidate at Virginia Tech in horticulture. My research is focused on the fate of nitrogen fertilizer and specialty crop production. I'll be graduating this fall and am interested in any and all potential opportunities after graduation. Today's session is on recent advances in LED lighting and controls. On behalf of the endowment, I'm excited to be a part of AFE's Grow Pro webinar series that features a new topic every month presented by an industry expert. The webinars are free to everyone thanks to generous support of AFE's sponsors. This session is sponsored by Ball Seed. Ball Seed is North America's leading wholesale horticultural distributor, combining extensive experience, innovative thinking, and world-class customer service. They source world-class breeding and product development that drives new sales, delight the consumer, and generate demand. If you'd like to learn more about our sponsors, or if you are a supplier and interested in becoming a sponsor for a topic, you can find that information and more about the webinar series on the AFE's website at endowment.org/grow, which is linked in the chat. Today's session was pre-recorded in English by Dr. Erik Runkle. After the presentation, Dr. Runkle will join us for a Q&A. Feel free to submit your questions throughout the Q&A feature or chat at any time. We'll answer as many questions as we can before the end of the hour. Unanswered questions may be answered through a separate email exchange. This session is being recorded and will be shared to AFE's YouTube account. Through YouTube's accessibility features, you can access closed captions in other languages. To get us started, I'd like to share a bit about today's speaker, Dr. Erik Runkle. Dr. Runkle is a professor and extension specialist in the Department of Horticulture at Michigan State University. He obtained a Bachelor's of Science in Ornamental Horticulture from the University of Illinois and his Master's and PhD in Horticulture at Michigan State University. Since he joined the faculty in 2001, he and his graduate research team have performed numerous practical experiments in greenhouse and indoor growing facilities to determine the effects of lights, temperature, and other environmental factors on plant growth and development. Experiments have been performed on a wide range of herbaceous specialty crops, including plugs and liners, annual bedding plants, and leafy greens. Dr. Runkle, welcome, and thank you for presenting today on recent advances in LED lighting and controls.
Thank you for the introduction. It's a pleasure to talk about some of the recent advances in LED lighting. These are the different topics I'm going to focus on today. I'll talk a little bit about photoperiodic lighting, which is the delivery of low-intensity lighting to regulate flowering. I'll then focus most of the talk on supplemental high-intensity lighting, and that's where we have the most questions and where LED lighting really has some advantages over conventional lighting. Under that parameter, I'll talk about the data light integral and effects specifically on young plant production, light intensity that's desired to obtain the desired results, light fixture efficacy, and that's one of the most important parameters when looking at different lighting fixtures. I'll talk a bit about the lighting spectrum and why that's important from both a plant and human perspective. And then I'll close with discussion of lighting control options and making sure that we maximize our use of supplemental lighting. And so the two of these different topics, I'm going to focus most heavily on light fixture efficacy and the lighting spectrum, because this is really where there have been the greatest advances in the last several years with LED lighting. So let's start off looking at just generalities about photoperiodic lighting and how it contrasts with a much higher intensity supplemental lighting. So photoperiodic lighting is specifically to regulate flowering of ornamentals. We're trying to inhibit flowering of short day plants like chrysanthemum or poinsettia, or we're trying to promote flowering of long day plants like petunia, snapdragon, or ageratum. The typical intensity delivered is relatively low. Typically, it's 1 to 2 micromoles per square meter in second. However, if someone is using boom lighting, you can see it's often delivered at about 25 to 50 micromoles. Conventionally, the type of lamp used was the incandescent bulb. Those have been phased out of production, and so now we see white LEDs, or more commonly red and far red LEDs, and I'll talk about that in a little bit. The lighting is delivered only at night when the days are short, typically from September through March, for about 4 hours, either at the end of the day or during the middle of the night. And compared to other types of lighting, this has relatively little effect on the shape or morphology of a plant. Contrast that with much higher intensity of light. Here we're trying to increase the growth, the quality, or the yield of a crop. Typically we'll get plants with more flowers, greater branching, and thicker stems. The value is greatest for young plants, at least from an economic standpoint, but also other high value crops where you can get a higher quality or a premium price for a higher quality plant. The typical intensity for ornamentals, 60 up to maybe 100 micromoles, and 2 to 3 times that for fruiting vegetables like tomato. Conventionally, high pressure sodium, or HPS, was the most common lamp type used, but now we're seeing those being replaced by LEDs. Typically, they contain red with white and or blue LEDs combined. This lighting is used at night, and when it's cloudy, they typically should not be operated when it's sunny because there's really no value in that. And again, when we're under relatively low light conditions, that will depend on the region, but oftentimes from sometime in September or October all the way until sometime in March. But that could be a little later or a little earlier depending on location. These fixtures operate typically much longer, up to 20 hours per day. And compared to other types of lighting, we have either no effect on the growth or architecture of a plant, or in some cases up to a moderate effect. And I'll talk about when we might see that. We have done a lot of research with photoperiodic lighting, really for the last 12 years at Michigan State, looking at different intensities, different delivery methods, and different light spectra. And this is a classic slide actually with Petunia Wave Purple Classic. It's a petunia that is relatively sensitive to photoperiod and to the quality or the color of the light. It has a relatively long day response. So on the far left, we see a plant grown under a 9-hour short day. And then 4 hours of night interruption lighting was delivered by incandescent bulbs, red and white LEDs, or LEDs that included red, white, and far red. And as you can see, the plant was vegetative under the 9-hour short day, as well as when day extension, night interruption lighting was delivered by the red and white LEDs. In contrast, when we had incandescent lighting, which includes red and far red light, or the red, white, and far red LEDs, you can see the earliest flowering. And so when we're under relatively light limiting conditions, you can see the daylight integral here is just under 6 moles per day. I'll talk about DLIs here a little bit later, but that's a relatively low light environment. And that's where we see this relatively strong response when we include light that has red and far red in it. We've also done work with different types of white LEDs, and this is just a snapshot and a good example with Snapdragon. Liberty Classic Yellow, it is a plant that typically flowers earlier under long days, but for a plant to perceive a long day, it has to receive an effective spectrum. So the plant on the left received a 9-hour short day, and then again we had 4-hour night interruption lighting from only red light, blue and red light, a cool white fluorescent or a warm white, cool white LED or a warm white LED. And then we had the red, white, and far red LED. And as the photo shows, the only light spectrum that was effective in promoting the flowering of the Snapdragon was the red, white, and far red. And again, this occurred when we were under relatively low light levels. So based upon a lot of research over the years, as well as some other studies performed by different universities, we have found that short day plants really respond to a broad range of light qualities or light colors, whether the light is delivered from incandescent or fluorescent, a high pressure sodium, for example, or even white LEDs. They're all effective at inhibiting flowering. The main thing, as long as they include red light, they are effective at inhibiting flowering of short day plants. And that contrasts quite a bit with long day plants, where when we're under low light conditions or a low daily light integral, Some of these bulbs are effective and others are not. So incandescent, the high pressure sodium, such as a beam flicker, or the red, white, and far red LEDs are effective, whereas lamps that do not emit far red light, such as the fluorescent or the white LEDs or the red and white LEDs, they're generally not or less effective. However, we see that the spectral effect begins to diminish when we're under a higher light, and so under a high daily light integral, and that would probably be more than 10 moles per day, all of these different lamp types are effective at promoting flowering. These are just a couple examples of commercial products that are available. It's not a complete list, but some of the major products out there. And these include both red and far red light. So for growers, especially in the north or in light limiting conditions who are trying to induce early flowering, these bulbs have all proven to be effective. Okay, so I do want to spend most of the rest of my time now talking on supplemental or high intensity lighting. Again, we are delivering a much higher intensity to increase growth, improve quality, accelerate flowering, and perhaps get even a longer post-harvest life when the plant is in the retail environment. So I want to go over daylight integral. We use that term a lot now. Sometimes we just refer to it as the DLI. This is what describes the total light intensity received per day. So technically, it's counting the number of photons or particles of light with a certain wavelength between 400 and 700 nanometers, and the amount of light that's received per square meter during a day. And so we can think about graphically the individual particles of light that fall within the square meter with light that has a specific waveband. And so we're counting this, we're measuring it with a quantum sensor, and the unit for DLI is moles per square meter per day, or sometimes we'll just simplify it as moles per day. So when we think about DLI, we think about really the total quantity of light, and this is how we quantify it. Again, we've done a lot of research over the years looking at daily light integral, and especially during the propagation stage. And this is typically when we see the most benefit of supplemental lighting when we're under light limiting conditions. This is some research performed by Roberto Lopez with me quite a few years ago, quantifying the effect of daylight integral on rooting, in this case of New Guinean patients. Here plants were stuck under different daylight integrals ranging from 1.3 up to about 11 moles per day. So we would be in a light limiting condition, less than probably 6 or 8 moles per day. And I say light limiting condition because the plants will root, the cuttings will root, but it takes much longer for the roots to fill the container compared to under higher light conditions. So you can see as you go left to right, you see a pretty linear increase in the rooting in terms of root number and root biomass, but it does begin to level out somewhere around 8 to 10 moles per day. And so that's typically our recommendation, is somewhere at least 6 moles and preferably 8 moles per day for a variety of different ornamentals. So this is work that just summarizes results with vegetative cuttings. We've done a similar amount of work with seedling production, where we've grown seedlings under different daylight integrals. 6 moles per day would be probably a typical mid-winter day on average. 10 moles per day we might be getting sometime in the early spring. And then 16 moles per day would be a relatively high light environment, something we might be getting beginning in the middle part of spring. And as you increase the light, in this case to salvia, you can see that the plants typically become more compact. The stems are a little bit thinner. The leaves are a little bit smaller, but probably most importantly, you can see that the rooting is much better under higher light. And so the plug becomes pullable earlier, and you can actually shorten your production time, in some cases by 1 to 2 weeks. So one of the questions we've received is, of course, lighting is expensive. To deliver this much light costs money. And growers have wondered, well, I can't afford to light my entire greenhouse or light all of my young plants, but if I can only light during a fraction of the production time, when do I get the most benefit? So we did some research looking at delivering high intensity light during different phases of the young plant production phase. And this first example I'm going to show is with pansy. The pansy production was 33 days from seed sow, and we divided that 33 days into thirds. And so we did not light at all at a high intensity, or we lighted these seedlings during the first third, the second third, or the last third of the production phase. As the photos indicate, on the left, the plants did not receive any high intensity lighting, and the plant on the right received high intensity lighting only during the last 11 days of this young plant stage. And what we generally saw in this and other crops is that the benefit of lighting was typically greater when it was applied later during this young plant production phase. So that would be only if you lit during 1/3 of the production phase. If you were to light plants for 2/3 during the production phase, typically the response was greater lighting during the latter 2/3 as opposed to the first 2/3 in terms of getting greater shoot growth and root growth. But what was best was if you could light the entire time. So really we're seeing a quantitative response with light where the more light you give it for a longer period of time, you typically see an increase in the quality and an increase in the growth. But if you don't have that luxury, then you get the greatest benefit by lighting during the latter part of the young plant phase. So these are results with pansy, and I'll just show you briefly results with a petunia. You'll see very similar trends where the rooting is greatest when under high intensity lighting the entire production phase, but you can still get a great deal of benefit from lighting if you're only lighting during the last 1/2 to 2/3 of the production phase. All right, so I hope I've communicated the value of supplemental lighting when we're under light limiting conditions. When I talk about how do we approach LED lighting in particular, although a lot of this would apply to high pressure sodium as well, these are kind of the different steps that you can take to determine or to go about investing in a lighting system. So one of the questions is, first of all, figuring out how much light you want to deliver. How much supplemental light do you have? Do you want to deliver? And I'll talk about that here in a minute. You need to understand your growing area, specifically the dimensions of your growing area and any constraints, such as the maximum hanging height above your crop. Once you have gathered information and you know how much light you want to deliver, you're advised to contact multiple lighting companies or lighting suppliers for specific quotations for your operation. I want to talk about efficacy because you'll often hear that term. People will talk about the efficiency of their fixture, and I want to put that in context. I want to talk briefly about LEDs and ones that are qualified by the Design Lights Consortium. A little bit about light spectrum and what things to consider. And then once you've considered these different factors and you have multiple quotations, then it'll hopefully, you want to compare the lighting solutions and determine which one is best for your operation. So one of the first steps is determine how much light you want to deliver. And this, of course, will depend upon what time of year you're lighting and geographically where you're located, as well as how much light is being transmitted through your operation. These are some old but still very useful maps that Jim Faust at Clemson University created. And they are color-coded based upon the average daylight integral, assuming light transmission 60% through a greenhouse structure. And 60% is a broad average. There are some greenhouses that certainly transmit more light, as well as the ones that transmit less light, but this would be maybe representative of a typical greenhouse. And so we are in a light limiting condition. Again, we would say when we're less than 12 moles per day. And when that occurs depends upon the location, but for growers in the northern half to 2/3, that means we're in light limiting conditions until sometime in March. So ideally, growers would be measuring their light intensity. They would have a quantum sensor, and it would be recorded by an environmental control computer, and they could basically calculate how much light they're typically getting throughout the year. If growers don't have this information, then these light maps are available, and I believe they are available through the American Floral Endowment website. So once you've determined how much light you have on average, especially during the darkest periods of the year, then you can determine what is your target minimum daily light integral. And it's very situational, and it's also somewhat subjective about what value you choose. But I put some listings here for different crop categories as a starting point. So based on research, we've seen that you want to deliver typically at least 6 to 8 moles per day for liners, for vegetative cuttings, probably 10 moles or more per day for seedling plug production. And then we're starting to finish plants, again, at least 10 moles per day for all of these crops. And when we're harvesting flowers or fruits, we typically want to deliver even more light. So depending upon what you're growing, other parameters like the spacing of the crop, as well as temperature, can alter these different suggestions, but at least this would be a starting point. So you have basically a determination of how much light you receive, what your target is, and then you want to deliver the difference between what you receive and what that target is. Now, to determine how much lighting you need, we've been talking about DLI, and that's again a cumulative amount of light received per day. But what's really important then is to deliver what intensity on an instantaneous basis do you want to deliver to achieve your desired light integral. So the PPFD refers to the photosynthetic photon flux density. It's really the light intensity that's delivered per second. And so the PPFD is, you can see some typical values for supplemental lighting would be at the low end around 50 micromoles. The high end for growers of fruiting vegetables or cut flowers would probably be at 200, maybe 250 micromoles. And the more intensity and the longer that you deliver or operate the fixtures, you can see the daily light integral will increase. So for example, if you're lighting for 12 hours per day at 100 micromoles, you would be delivering a supplemental daily light integral of 4.3 moles per day. So based upon how crops respond to light, as well as economic considerations, an average or a typical grower, especially of young plants, who is going to be enriching the light with LED lighting, will deliver somewhere between 75 to 100 micromoles and operate those fixtures from 16 up to 20 hours per day, depending upon whether it's sunny or not. And so with that, you can supplement the DLI anywhere from 4 to 7 moles per day. So let's talk specifically now, once you've determined about how much light you want to deliver, I want to get into some of the technicalities about LED lighting. And LED lighting, really, one product is often very different from another. When we talk about LED lighting fixtures, we're thinking about them as in terms of emitting different intensities of light and different colors of light, and also they have different energy efficiencies. And all of these are influenced by the individual makeup of the LEDs. So we have LED fixtures that contain multiple LEDs. They could be dozens or hundreds of them on a particular fixture, and they're usually composed of blue, white, and red LEDs, and occasionally you'll see some far-red LEDs in a fixture. This is a graph that my graduate student Jiyoung Shin just recently created, looking at the photon flux efficacy, which is the efficiency of a LED. And it varies not only from one color to another, but from one wavelength to another within a particular color of light, and also from one manufacturer of an LED to another. So what we have here are different efficacy values, where the higher the number refers to a more efficient delivery of light per unit of energy consumed. So we have, among these different 4 types of LEDs, the least efficient are the white LEDs. Close to that would be the blue LEDs, and then the red and far-red LEDs are the most efficient. And you can see that there is also a broad range in the efficiency of the red and far-red LEDs. Actually quite a dramatic difference from potentially from one type of LED to another. And so this will vary by the manufacturer as well as other considerations. And so when we look at the efficacy of a fixture, it really depends upon what types of LEDs are in the fixture, as well as what are the wavelengths and what is the LED manufacturer that is in that sort of LED fixture. So there are other factors that influence the efficacy of an LED. It's not just the actual color like I've talked about in the last slide, but it depends upon how hard the fixture is driven in terms of how much energy or what current are you delivering it and how much light is being emitted by that LED. So the energy efficiency depends not only on the LED color like I showed in the last graph, but also the current density. And you can see what the theoretical maxima are for these different types of LEDs. So the theoretical maximum for a blue LED is around 3.7 or 3.8 micromoles per joule. And if we drive that LED at a relatively low current density, we have current LEDs that are getting close to that theoretical maxima. The theoretical maximum efficiency for red LEDs is quite a bit higher, around 5.5. And we still have a little ways to go, but again, we're getting some pretty efficient red LEDs that are now already available. So a couple things is that as we increase the power to these LEDs, in other words, as you increase the current density, you get greater light output. So the light is brighter, which means that you would need fewer LEDs to deliver a certain light intensity. The consequence of that is that you would need fewer LEDs on a fixture, which could potentially decrease the cost of that fixture. The con, however, is that as you increase that current, you get a decrease in the efficiency of the fixture, and also the lifetime of the fixture typically goes down. So what you end up with is a trade-off between the number of LEDs in terms of cost on a fixture and the efficiency and lifetime of the fixture. And so LED lighting companies will typically find some sort of intermediate zone where you get a fairly high light intensity without powering them too much so that the lifetime is still reasonably good, as well as the efficiency. So when we talk about a fixture efficacy or the efficiency, this is not something that most people can measure. I cannot measure it unless I had this sophisticated equipment, which I don't. And so it really refers to capturing how much light is being emitted by a device divided by the amount of energy that's consumed to emit that amount of light. So lighting companies, the larger ones at least, will have these sorts of instruments, or there are also independent testing labs that are able to quantify the light emitted by a device and then also measure how much energy is being consumed during that process. So this is something, again, that would be coming from the lighting manufacturer or a retailer of lighting a product, and it's not something that we can measure. And actually, a relatively small number of people have this integrating sphere that are capable of quantifying these different efficacies. So fixture efficacy is very important because it refers to the efficiency of the fixture at converting energy into light that's useful for plants. And so to do an example of a calculation, if a lighting company had a fixture and it emitted 600 micromoles per second, as measured by that device I showed you on the previous slide, and in the process it used 300 watts. 300 watts is the same as 300 joules per second. It's simply a division of the amount of light delivered by the energy consumed, and the unit becomes micromoles per joule. So in this case, it would be 600 divided by 300 to get an efficacy of 2.0 micromoles per joule. And again, the higher the value, it means the more efficient the fixture is. There is fortunately a lot of information now on the efficacy of fixtures, and this is one of the major reasons why we are seeing more and more adoption of LED lighting. Shown up here are the efficacies of conventional high-pressure sodiums, and until about just 5 years ago, these were still the most efficient lamp types for plant production. And so the efficiency varies upon whether it's a magnetic or an electronic ballast, as well as the power that is going to the device. So the efficacies range from about 0.94 for a 400 watt magnetic high pressure sodium, and then about twice that for a double-ended high-pressure sodium with an electronic ballast. So this would be kind of the range of what we see growers use, and actually we still see a lot of greenhouse growers with the traditional 400-watt high-pressure sodium magnetic ballast. Let's contrast that with LEDs that are available today, and I just selected some of the many that are out there. There are literally hundreds of different types of LEDs available on the market. These are ones that I chose from relatively well-known LED suppliers or manufacturers. And what it shows is on the left column, the photosynthetic photon flux, that refers to the amount of light emitted by a device, and then the efficacy, which is in the right column. So we're seeing that the amount of light emitted by a fixture varies widely from whether it's a high pressure sodium or an LED, and the efficacy also varies quite a bit. But fortunately, we're seeing these LEDs now are usually at least 50% more efficient, and in some cases, much more than that. So this will just give you some idea about how LEDs are in terms of energy efficiency. And I also want to point out it shows how inefficient the old 400-watt high-pressure sodium magnetic ballasts are. So this data has been generated by the lighting companies. They often will supply this to the Design Lights Consortium. The Design Lights Consortium is a nonprofit organization that is basically trying and has developed standards for horticultural lighting to ensure that there are products out there that meet some minimum performance specifications. These are the current DLC technical requirements. So a lighting company can perform testing, and if they meet certain criteria, they can become a DLC qualified product. And I think that's important because these are basically the minimum standards that have been established for a relatively high performing LED. So the minimum, to become a qualified product, the minimum efficacy value is 2.3 micromoles per joule with a tolerance of 5%. But also the LEDs must last a certain period of time. In this case, the light intensity must not decrease more than 10% after 36,000 hours of operation. That's referred to as the Q90. And the driver, and if the fixture has a fan, they must last at least 50,000 hours of operation. Importantly, they must also have a 5-year warranty and be safety certified. So these are just some of the different requirements that I've listed. I think these are the more important ones in terms of the energy efficiency and the longevity of a fixture. So for those who might be interested in learning what products are qualified by the Design Lights Consortium, you can go to their website. They do have different types of lighting, but the one we want to focus on is the horticultural lighting. They do require that you register before you search the qualified products listing, but it's free and it only takes a minute or two. And so there is a lot of information on this website that you can use to try to learn more about different types of LED fixtures that are on the market. Okay, so given all the different lighting fixtures that are on the market, we have literally hundreds of them available. The last I checked, there are over 1,000 qualified products on the DLC website. And they can vary a lot, right? And not only in terms of dimensions, but the amount of light that's delivered, as well as the color of the light. And so one of the questions that I'm often receiving is not only what intensity of light do I deliver, but what color spectrum do I choose? And it is going to be subjective and situational. One of the things it depends upon is when you will be delivering the light and how much light you're receiving from the sun. So based on research that I and my colleague Roberto Lopez has done looking at the daylight integral in the greenhouse that we get from the sun combined with enriched light from LEDs, we have learned that when we're under light limiting conditions from the sun, less than 8 moles per day, that the spectrum of LED lighting can actually influence the shape and the architecture of a plant, as well as the pigmentation of the leaves. And specifically what we key on is the percentage of blue light. And so an LED fixture that emits a moderate to high percentage of blue typically will create plants that are more compact, have smaller leaves, and the leaves will be a darker color. When we have more sun, when we're under light integrals higher than 8 moles per day from the sun, we typically see a diminished effect of the LED spectrum on the growth of the plant. So the LED spectrum really is important when we're under the darkest days of the year, and that will depend upon location. It'll be several months of the year for those in the north and in Canada, and a much shorter period of time for those in the south. But when looking at an LED spectrum, we often want to key on the percentage of blue light that is being emitted. So I pulled the light spectrum for just 3 examples of LED products that are on the market. What they do is show the basically the peaks or the distribution of light that is being emitted by the particular product. So what we can do is divide these into the different regions of light. We typically think of light as blue, green, or red, simplistically, and we focus again on how much is in the blue region. We don't only focus on blue though. So when we look at LEDs, a large percentage of them emit a lot of red light. And a reason for that is because they're so energy efficient compared with other types of LEDs, as I've discussed earlier. And so we can see on the left an example of an LED that emits only blue and red light, or on the middle and right, we can see some examples of fixtures that emit or are composed of red and white LEDs. And so when we have a blue and red LED, there's no green, and the light appears purple to us. And then as we increase the amount of white LEDs in a fixture, the light obviously becomes whiter, and that's because we have more and more green light. Most LED fixtures, again, contain red, and then they are supplemented usually with white or sometimes with just blue LEDs. If we're looking at green light, the green light is usually delivered by the white LEDs because green LEDs by themselves are very energy inefficient. And typically the more green light that we would see in a graph like this, the whiter the light will appear to us. One of the things we have seen recently that, again, my colleague Roberto Lopez and I are learning about is plants that develop this sort of necrosis when they're grown under LED lighting right after sticking. And specifically, we have seen that plants grown in the cooler temperatures typically have a more pronounced discoloration. And so this is not necessarily something to be alarmed about. We are learning more, and we'll be sharing more information with you shortly. Now, in terms of visual quality, I mentioned this before, but when you only have an LED that includes red and blue LEDs, we create this purple spectrum, which creates a challenging environment for people to work in. And so for that reason, we typically recommend that a fixture contains at least some white LEDs so that workers can have a more pleasant environment. Okay, the last several slides will be looking at maximizing use of supplemental lighting. What I want to draw here is basically how plants perform photosynthesis in relation to the light intensity. So on the left, we have net photosynthesis, and on the right axis, we have light intensity. And this is just a typical shape that will depend upon a number of factors, not only the plant, but the temperature and whether there's carbon dioxide enrichment. But you can see that the photosynthesis rate increases with the intensity of the light, but it begins to diminish as we increase the light intensity. We have a, we have a light compensation point, which is basically where the light intensity is just sufficient so that there's no loss of energy from the plant. And then we also have a light saturation point, which is where we're approaching the maximum use that a plant can use light. Within this region, I want to talk about what is the value of supplemental lighting. Because of the shape of this curve, we can see that if we were to supplemental light, in this case 75 micromoles, we get a relatively good boost in net photosynthesis, which would result in a significant improvement in growth. But when we add that same 75 micromoles to progressively higher intensity of sunlight, you can see that these benefits begin to diminish. And so for these reasons, this is why we use supplemental lighting at night or when it's cloudy. And really, there's no benefit of using supplemental lighting when it's sunny outside. So with that in mind, these are really the three different options to control lighting. One is with a time clock, which I won't talk about because it's the least desirable. And that's because it can result in the lights operating when it's sunny. And again, there's no value of doing that at that time. What's much more common is using controls based upon instantaneous thresholds, as well as there are attempts to have more sophisticated controls with lighting to target a specific daylight integral. So looking at lighting controls and the most common way to turn lighting on and off requires a control system for your environmental control system. It requires a quantum sensor that is usually part of that. And so basically it's measuring light, and when light is above a certain value, the lights turn off, and when light is below a certain value, they turn on. The position and the location of this quantum sensor is extremely important because this is the signal that's being used to operate the fixtures. So it should be clean, it should be level, and it should be in a representative location, not shaded, for example. Preferably, this would be a quantum sensor that is inside a greenhouse, but it's much more common to see these outside. And so that's something that we need to work on, is learning where to put these quantum sensors to get the best results for LED lighting. The set points for LED lighting can be different than they were for high pressure sodium. And one of the major reasons is that the longevity of LEDs does not diminish with on-off cycles. Whereas with high pressure sodium, they have a warm-up time and their life cycle degrades as they turn on and off. And so one can imagine much more frequent on and off cycles with LEDs than would be appropriate for high pressure sodium. And at the bottom, I just list what an example might be, that a light fixture would turn on when there's less than 300 micromoles for a short period of time, and then they would turn off when the light level is above a period of time above a certain value for a period of time. As I said, there have been some attempts for dynamic lighting control. These have unfortunately been very challenging. I think it's a great goal to have where you're trying to potentially dim LEDs or turn them on and off depending upon electricity and other factors, including potentially the weather forecast. But efforts so far have shown this to be very difficult for various reasons. And one of them has been with challenges in compatibility with environmental control systems. So with that, there are more resources for information. This is a plant lighting book that is written by 20 different leading experts in plant lighting, targeted for growers, college students, and lighting representatives. It's available through Amazon, and it was edited by me and Roberto Lopez. We also have a lot of information on our floriculture website at Michigan State University. In the middle row on the right, you can see there's a tab on light management and controlled environments. And so if you're looking for more specific information, this is a resource. I would like to conclude by acknowledging the different granting agencies, including the American Floral Endowment, the Floriculture and Nursery Research Initiative, the USDA, and many different greenhouses and lighting companies that have supported our research, as well as allied trades that have provided donations and in-kind of both cash and of products. So with that, I would encourage you to participate in the next Grow Pro series. That'll be on Tuesday, June 20th by Dr. John Dole. And you can see to register, there's information on this screen. So I would be happy to take your questions. And again, thank you for your participation.
Dr. Runkle, thank you for your presentation. And I'd like to open up the session for questions and answers now. So our first question is, and I think this goes back to one of the first experiments you were showing. It says, what's the distance from the light to the top of the plant you typically go for?
You know, we actually rarely measure that, because what we do when we place lamps or place plants is we are targeting a specific light intensity. So we position the fixtures based upon the intensity that we're trying to deliver I would hate to give a certain distance because an appropriate distance would depend on a number of factors. But ultimately, distance is a function of what intensity you're trying to achieve.
Okay. Our next question is, what type of fixtures are you using for your research?
We use a broad variety of fixtures. Some of them are experimental. Others are ones that we're looking for a specific spectrum. So we have several different manufacturers and multiple generations of fixtures. We do work a lot with Philips, but we have some other companies that we've worked with. Lumigrow, that's unfortunately no longer in business. We've worked with some PL light fixtures. So we're careful not to align ourselves with a specific company, but we have tended to work more with Philips fixtures than probably any other at this point.
Okay. So our next question is there a response with supplemental lights in the tropics, for instance, Colombia or Ecuador?
Is there a response? Yes. Is it economical? Probably not. And so in those locations, those are highlight regions. And the benefit of adding light to already a highlight environment would be trivial and likely not worth the cost to purchase or operate the fixtures. Now, there could always be exceptions. But if you're in those countries and you're able, you don't have anything like a really dark greenhouse or something to contend with, I would not expect a compelling reason to use high intensity lighting. Now, supplemental light can also sometimes mean photoperiodic lighting, which is delivery of low intensity light to regulate flowering. And in that case, if you're trying to promote flowering of a long day plant, then creating or adding light on at night can have value. So that again would focus on whether you're trying to regulate flowering. If people are trying to produce stock plants, for example, they will try to inhibit flowering so that cuttings are vegetative. And so in some cases, depending on the crop, you'd actually want to deliver short days. In other cases, there'd be value in delivering low intensity photoperiodic lighting.
Okay. So our next question is, you mentioned the theoretical maximums for LEDs. When do you think those will be achieved?
So we can look at how LEDs have advanced over the years, and they continue to advance technologically, but I think each year we're seeing less and less advancement. So in other words, if we look back, what has happened every year the last 5 years, we've seen some significant gains in efficiencies. But the last couple of years, those gains have been relatively small compared to previous years. And so for that reason, we're probably 5 to 7 years away from approaching the theoretical efficiency. We probably will never get to that because, again, that's theoretical. Depending upon the LED, I think we're already 80 or 85% of the way there. And so I know that's been a reason why some growers have now invested in LEDs, because they're worried that they buy something today and it'll be out of date in 2 years. And I think that was a legitimate hesitation 5-7 years ago, 10 years ago especially. But I think that is becoming less and less of a compelling reason, because we're going to just see smaller and smaller gains in the next several years.
Okay. Got another question here for you. I want to use LEDs for propagation and finishing. Which spectrum is best for this?
Spectrum is very situational. So in the talk I mentioned, obviously there are people concerns about working in a purple light environment. When I think of a spectrum, I often focus on the percentage of blue light, because blue light has a big role in regulating extension growth. And so if you're trying to produce plants that are more compact, which is often the case in propagation, you'd probably want a spectrum that has at least a moderate percentage of blue. And moderate can mean many things, but it could be 10 to 12%, for example. Now, having said that, if you're not trying to inhibit extension growth, and let's say you're producing cut flowers and you want long stems, that could be a case where you want a low blue light percentage. So I guess it really depends on what are the sorts of attributes you're trying to achieve. And then those are the types of conversations I think that are useful with lighting providers to discuss them, what your goals are, and try to come up with a suitable light spectrum.
Okay. So our next question is, I can get a good deal on some used LEDs. Is there anything I should consider before buying them?
Yeah, you'd want to know certainly how old they are. Ideally, you'd want to know how many hours they've been used, but that could be impossible to find out. But at least knowing how old they are would be useful to know, so you can gauge how much lifetime they still have in them. I would also try to find out if that particular model, if it's not available today on the market, if it was a product that was qualified by the DLC, which I mentioned in my talk. That would be desirable because you'd have some assurance of it being well constructed and able to tolerate a greenhouse environment. So greenhouses can be humid and dusty, and those are challenging environments for LEDs that are not properly sealed. So yeah, I guess the more information you can know about the fixture, the better. I would probably tend to trust a manufacturer you've heard of before, as opposed to some used LEDs from a company you've never heard about. It doesn't mean that those aren't necessarily poor quality products, but I think it would help ensure that maybe the fixture was made to be durable if you've heard about the company and they're still in business today.
Okay. So our next question is, have you considered research for eye protection for workers in red, blue lighting, or know if such products are effective?
So we are concerned about blue light, and even more so UV. In the greenhouse, we typically are not delivering UV light, although there can be an exception. Blue light, has been a lot of research done by people with that expertise that I don't have about potential hazards. And the biggest hazard is actually looking at a blue LED for a prolonged period of time. Blue light has high energy, and if we look at it, it may not appear very bright to us because of how we perceive light. And so staring at a blue LED would be a very bad thing, especially if you do it for a prolonged period of time. In that case, I think you rarely see a blue LED used alone. It's almost always mixed with white or red LEDs. And so you end up having a pretty high intensity light anyway, which really prevents people from staring at a light. I mean, it would be similar to staring at any other highlight source that you just would not want to do it. Having said that, there is a concern with blue light, and there are safety glasses that block out the UV and the blue. And those can be worn in situations where people are concerned or want eye protection. You can buy those sorts of glasses for $8 or $10. They do take out the blue light, and so it can, depending upon the other colors in the spectrum, it can create more of a yellowish type of light. But that would certainly be a way to be abundantly cautious if you're worried about blue light and eye protection.
Okay. We've got one more question. I saw a grower using day-length extension lighting in his propagation house. He said it increases rooting. Can that be true?
So day-length extension lighting would typically be low-intensity lighting. So we have low-intensity lighting that is usually not sufficient to stimulate photosynthesis, and therefore you typically would not get a growth response like better rooting. Now, there can be, I would say, an indirect promotion of growth by growing plants under a long day versus a short day. And I mention that because under long days, plants often develop larger leaves. And if you have a larger leaf, you have the ability that plant can actually capture more light, which then can lead to larger growth. And so there potentially is an indirect effect at delivering low intensity lighting and increasing growth. But I would say that that indirect effect and the promotion of growth would likely be considerably less than if you installed a high intensity light to stimulate growth.
Okay. Well, that was our last question, so I'm going to close this out. Thank you, Dr. Runkle, and thank everyone else. Thank you for joining us for another session of AFE's Grow Pro webinar series. Join us on June 20th at 1 p.m. Eastern Time for our next session on current post-harvest handling recommendations for cut flowers. Visit endowment.org/GrowPro to see our full list of upcoming sessions, past webinar recordings, and other grow-related resources and research reports, all of which are available to you free thanks to industry support. If you find this webinar series and AFE's other industry resources valuable to your business, please consider making a donation to our 2023 annual fundraising campaign. This campaign just kicked off yesterday and will run from now until June 30th. For more information about this year's campaign and sponsorship information can be found at endowment.org/rise. This will be linked in the chat. We also ask that you please complete the brief survey about today's session where you can suggest additional topics and help us continue to improve these webinars. Thank you all again for joining us.
Thank you.